That's going. All right, so what have we been talking about this semester? What are the main ideas? This whole semester we've been focusing on more or less one concept. What was that? Motion. Vectors are an important part of motion. When we talk about motion, what physical quantities come to mind? All right, share with your neighbor what physical quantities come to mind when you think about motion. Turn to your neighbor. I'm going to call on someone that I don't see talking to their neighbor. All right. In the back, what comes to mind when you hear the word motion? Velocity. What does velocity mean? A position over time. Sure, we can call it position over time. More accurately, we might say velocity is the change in position over time, right? We want to specify what you mean by position, right? Because when we think about position has a very distinct physical meaning, right? When we hear the word position, what do we think? In the gray sweater right here, what do you think of when you hear position? What does that mean? Not necessarily distance, right? Position means something else. What's position mean?
Final minus initial.
No, that's displacement, right? So position means what?
The location of the object.
Location of an object, right? Position is the quantified location of an object. Now, when you take that quantified location and take the final location, subtract off the initial location, you take the final location, subtract off the initial, and what do you have? Displacement. Displacement is your change in position, right? Going back to this idea of velocity. Velocity is your change in position or your displacement over time. That's absolutely true. So we have position. Change in position is displacement. Change in displacement over time, the rate that your displacement changes, that's velocity. And oftentimes we call this quantity of velocity, we say that that is, in essence, our motion. Because that is what describes our motion in any given time. It tells you how fast you're moving, in what direction, right? But if you have that velocity changing, right? If you have that velocity changing, we often call this non-uniform motion, changing velocity. If you have that velocity changing, what do we call that? Acceleration. So we often say that if you are accelerating, your motion is non-uniform. Non-uniform is just a way to say changing. So your acceleration indicates non-uniform motion. And today we're going to be focusing on that idea. On that idea that acceleration is a description of how your motion changes over time. We might write delta V over delta T if this is a constant acceleration. If it's non, then we take the calculus version, dv dt, right? The derivative of velocity with respect to time. That is just to say your motion is changing as time progresses. So we feel okay about this, right? And we've been describing motion as though we did not care about the causes of motion, or more importantly, the causes of changes in motion. We've been talking about this acceleration, velocity, and this displacement, but we haven't really talked about, what makes something move. What are the causes of motion? That's the difference between what we call kinematics and dynamics. Kinematics, we have the acceleration, velocity, and displacement, position, all those things. We have those and consider them by themselves. Now we are going into the realm of what we call dynamics. And I didn't finish this DT. Now we are going into the realm of dynamics, where now we're asking the question. We have a way to describe motion, but what causes that motion, right? Getting into this realm of dynamics. The causes of motion. And why do we do that? We do that because acceleration, position, velocity, all of those things, those are our descriptions of where an object is. We want now a way to predict how an object will move, given us doing something to that object, right? So it's all about making predictions. If we can predict what is occurring to an object, we can predict where that object will end up. So dynamics is this idea of now taking this one step back, saying, if I know what causes motion, then I can predict where an object will be in the future. Now, in order to study this motion, I brought in this neat little toy. I shouldn't say it's a toy. I found this in our back room, and it's nice. It analyzes motional quantities. It analyzes position, velocity, and acceleration. We'll be using this momentarily. But before we get on to the actual measurements, I want us to take a look at that red cart. When we look at this red cart, we can say its velocity is currently what? 0. Okay, so we're going to wait a couple of seconds. All right, what is its velocity now? So we might say something about its motion, right? Its motion, its velocity. What can we say about its motion? It's at rest, certainly. But can we say something more about its motion over time? It's not changing. It's not accelerating. It's not changing. Right? The motion's not changing, which means the acceleration is 0. So we have this object here, this red cart. It is stationary, and it will remain stationary. But what if I don't want it to be stationary? What do I have to do? You have to apply a force. You have to give it a push, right? In other words, you have to interact with it, right? As long as I am not interacting with this cart, it won't move. It won't move if I'm not interacting with it. So what does that mean? That means that these interactions, I have to interact with the cart, and if I interact with the cart, only then will I get a change in motion. Interactions cause changes in motion. Interactions cause changes in motion. And what is an interaction? Well, broadly speaking, interaction is just some sort of a push or a pull on an object. Now, the ways in which we can push or pull an object, well, there's numerous ways, there's numerous types of interactions, but it all boils down to this idea that if you interact with an object, that object might move. And if it might move, well, that means if it might change velocity, well, then it's accelerating by definition. So interactions cause changes in motion. Interactions cause accelerations. Does that seem all right? So interactions cause changes in motions. And the way in which interactions cause changes in motion, well, these can be studied through what we call Newton's 3 laws, Newton's laws of motion. The laws of motion tell you about how an interaction might cause a change in motion. How an interaction might cause acceleration. Sound good? So we start off with Newton's first law. Newton's first. I hear the person outside. Does anybody else hear the person outside? All right, so we have Newton's first law. Newton's first law of motion describes an object, but specifically an object in which there is no, I'm going to use the phrase, net interaction. There is no net interaction. And I use that word very specifically. So, in order to analyze net interaction, we're going to look at this cart and again do an experiment. Right? We look at this cart, we do an experiment, but this time let's start applying numbers because numbers are fun. So I'm going to come over here. I'm going to realize that my cart disconnected, so I have to come back over here, turn it on. times, right? The first part we can do before it connects. All right, so we repeat the experiment from earlier while this connects. And when we look at it, we say its velocity is 0. We wait a little while, its velocity is still 0. With no net interaction, we can look at this and say its acceleration is what? 0. Perfect. But what happens if we allow it to move? So I'm going to press record here. Of course, it's going to say 0 velocity, 0 position, 0 acceleration, all that stuff. I'm going to give it a little bit of a push here. And as I give it a push, we're going to look at the motion. Now, didn't do a great job there. There's a lot of friction here. Give it a little bit of a push, and we see that its velocity is roughly flat line while it is moving. Now, it does slow down a little bit. But you get roughly a flat line of velocity versus time. And in fact, if there's no friction, the velocity versus time would show a flat line. A flat line on a velocity versus time graph indicates what about the acceleration? 0. So even while it's moving, ideally, even while it's moving, if there is no net interaction acting on this object, the acceleration is equal to 0. So Newton's first law says acceleration is equal to 0 if the net interaction is 0 as well. This is just a way to say if you don't interact with an object, it will not change its motion. This could mean that it is moving. It just means it won't change its motion. It won't accelerate. This is Newton's first law. Acceleration is 0 if the net interaction is 0. We'll talk more about what that means exactly. What net interaction means exactly. But that's just one of Newton's 3 laws. His second law is a little bit more important, a little bit more interesting to look at. Because Newton's second law answers the question, Newton's second law answers the question, what occurs when we have an interaction? What occurs when something is pulling, pushing on an object? And we might be able to guess. If no interaction means acceleration is 0, well then what might happen if we interact with the object? It's going to have some acceleration. Its velocity is going to change. Perhaps the acceleration changes as well. If the acceleration changes, the problem becomes a lot more difficult. But perhaps that's true. So what are we going to do here? We have our acceleration versus time. I'm going to zoom in a little bit. I think I can zoom in here. Or perhaps I can't. Zoom. Clearly it's not going to let me. But we should still be able to analyze this. So I'm going to put this at the end. What I'm going to do is I'm going to take this weighted hanger and put it over the edge. What's going to happen is this hanger is going to pull on the cart, yes? So we look at the cart. We say, what is the velocity of the cart right now?
0.
0. Okay. So then if it starts moving, then its velocity changed, right? So if I let go of this and it starts moving, that means the pull of this hanger accelerates the cart. Let's go ahead and see if that happens. Yeah, it accelerated. In fact, you can see the acceleration here. You can see our change in velocity. We go from, roughly 0 velocity up. We have some change in velocity. So the weighted mass accelerated the cart, right? Now we keep that in mind. We keep in mind the acceleration that we just had. In fact, I'll rerun the experiment for us. Why not? Here's the cart. We're going to accelerate it. Everybody pay attention, though. I want you to pay attention to how fast the cart gets. Okay? So we look at it. Moves relatively fast. But what if I wanted to put a larger pull on it? All right, let's put some more weight on it. If I put more weight on it, what do we think might change about the acceleration? Increase, maybe. Maybe we see an increase in acceleration if we increase the amount of mass I hang off the edge. Why might that be the case? That might be the case because the string would be pulling harder, right? So let's go ahead and let's see. Does it accelerate a little bit more quickly? Does the velocity change more quickly? Was it moving faster? Yes. Indicating more acceleration. So what does that mean? That means the stronger the interaction, the larger the acceleration. Stronger the interaction, larger the acceleration. So increased interaction results in increased acceleration. Sound good? Increased interaction means an increase in our acceleration. All right, let's run another experiment. First, what we're going to do is we're going to look at our original scenario. Here we have the original amount of weight hanging off the edge and our cart. We're going to run this again just to get an eye on the acceleration to see how quickly it accelerates. So let's go ahead and let it do so. So you see how quickly does it begin to move? Moves relatively fast. All right. Well, what happens now if I take the same cart, same amount of force, but this time I'm going to increase the mass of the cart? What do we think happens if I increase the mass of the cart? Decreased acceleration. It doesn't move quite as fast. Let's see if that happens. Yeah, that didn't move nearly as fast, right? So what does that mean? That means that an increase in mass seems to lead to a decrease in acceleration. An increase in the mass, the amount of matter that is present for the cart or for whatever object we're looking at, an increase in mass seems to lead to a decrease in acceleration. We need more board space, and this cart didn't work out nearly as well as I hoped. Maybe we'll. So we have these ideas. We have these ideas of Newton's first and second law, where it says if you have no interaction, there's no change in motion. And if you have a larger interaction, that means a larger acceleration. And if you have a larger mass, then a decrease in acceleration. So we go through all this. Why do we go through all of this? We go through all of this because we want a way to determine the acceleration of an object given whatever it is that is interacting with the object. And once we have that acceleration, we can determine velocities. So if you know the interactions, then in theory you should be able to tell the acceleration. If you know the acceleration, you should know your velocities and your changes in velocities. And if you know your changes in velocities, well then you should figure out positions and you should be able to tell where an object will be based on the interactions that occur to an object. But then that opens up the question. Sure, we can figure out the motion of an object given the interactions, but what is an interaction? What is an interaction? Well, interaction can be easily spoken about. We can easily say an interaction is any sort of a push or a pull on an object. An interaction is any sort of a push or a pull on an object. But how do we push the object? How do we pull on the object? That's where the difficulty in defining these interactions begin to occur. How do you push an object? How do you pull on an object? Well, we can think of one very obvious way of how an object is pushed or pulled, right? If I take this mass and I let go, what's going to happen to it? It falls to the ground. Why did it fall to the ground? Because of gravity. So we could say gravity pulled on that mass, right? So we can talk about this interaction of gravity. This interaction of gravity, which might push or pull on an object. Sound all right? So we have this interaction of gravity which pulls on objects. Now we ask the question then, what is this an interaction between? Because this word interaction means two things are interacting with each other, right? We have two things interacting. Every interaction is between two objects. Now you take this mass and you drop it. Well, the mass is one of the objects that are interacting, but what is it that's pulling through gravity? What pulls this to the ground? Yes, the interaction is gravity, but what is causing that gravitational pull? Any ideas? What causes gravity? The Earth. The entire Earth, in fact, not even just the center. So gravity is an interaction between the entire Earth and an object near its surface. Technically, any object would be pulled on by the Earth, but we'll keep it in the context of near the Earth's surface. So the gravitational interaction is an interaction between the entire Earth and whatever object is near its surface. When we think about this, we say the entire Earth pulls on an object through this gravitational interaction. Okay, we can ask more broadly, what is the Earth pulling on? Well, the Earth is pulling on that mass. The Earth is pulling on me. The Earth is pulling on the table. The Earth pulls on everything near its surface, right? So we take a look at this little red cart, right? Does the Earth pull on this little red cart? Yes. As evident by the fact that if I let go, it's going to fall to the ground, right? So we all agree Earth is pulling on this red cart. I put the cart right here. Is the Earth pulling on it? Okay. I put the cart on the table. Is the Earth pulling on it? Yes. The Earth is always pulling on this little red cart. Unless you take it out to the middle of space, light years and light years away, the Earth is pulling on it. So the Earth is pulling on this red cart, meaning that there's an interaction present, right? There is an interaction present. The Earth is pulling on the cart. That is an interaction. Yet, we see no acceleration. Why not? Why do we see no acceleration?
There's an opposing force.
There's an opposing interaction. We're going to use the word interaction for a little while. I'll explain force in a moment. But there's an opposing interaction, right? There's an opposing interaction. And this interaction is what? Well, we look at this and we say the table is in contact with the cart. When you have contact, that usually indicates an interaction, and that is the case here. You have an interaction between the surface of the table and the cart. We call this interaction a support interaction. Support interaction. Why do we call it that? We call it that because the table is supporting the red cart. If I were to stand on this table, the table would be supporting me through the same type of interaction. We call this a support interaction. So we have multiple interactions. And when we combine these two interactions, we say we have a net interaction. When we combine these two, our net interaction is zero, giving us zero acceleration. So what is a net interaction? It's the combined effect of all interactions acting on an object. The net in physics means the combination of all interactions acting on an object. So the support interaction, then, we can say a support interaction is an interaction between a surface and an object on that surface. That sound all right? All right. What other interactions can we think of? What other pushes or pulls might we see? Who has an idea? Any other interaction? Any other pushes and pulls that we might see? Have we seen one today? You just scratching? Weight or mass? Now that's interesting. That's interesting. This idea of weight. This idea of weight, as we'll see, is actually a gravitational interaction. You step on a scale, the scale tells you your weight. What is it reading for you? It's reading how hard is the earth pulling on you. That's why you go to the moon, you would see you have a different weight. You go to Mars, you have a different weight. Your mass would be the same because you're not changing the amount of matter. But you have a different weight. So this gravitational interaction, well, that's actually what we would call weight in sort of day-to-day terms. So we'll get more to the distinction between the words weight and gravitational interaction. That's excellent. That's excellent. Any other ideas?
Another object interacting with that object.
Sure. We take a look at this cart. I am an object. This cart is an object. I can interact with the object by pushing it. When I push it, I'm interacting with it, and we give this sort of general interaction the name, I'm going to use the word applied here, an applied interaction. Generally, we reserve this for being a catch-all term for anything we don't have a great explanation of otherwise. But this is an interaction that we would generally term as an object and an object interacting with one another. That is absolutely true. What other interactions have we seen? Well, if we take a look at this, if I apply a little bit of force to this string, the string pulls along the cart, yes. String can interact with an object. We have string interacting with an object. That is a tension. Tension. A tension is a type of interaction that occurs between a string and an object. Sound good? Take this cart, flip the cart over so the wheels are up top. You're going to give it a push. It comes to a stop. Why does it come to a stop? Friction. Friction is another type of interaction. An interaction you have to deal with over and over. Friction. Friction is an interaction as well. Well, what is it an interaction between? We have the table sliding across the cart sliding across the surface of the table. Friction is an interaction between surface and object sliding. Technically, we can describe rolling and stationary friction. Sliding across that surface. What do we notice about that pair, though? What do we notice about that pair? Any ideas? Have we seen this pair, surface and an object on the surface? Right? For it to be sliding across the surface, that object has to be on the surface. Have we seen this pairing of interacting objects? The support force. The support force and the friction force, these two, interactions, not forces. I'm done. The support interaction and the friction interaction, these are between the same two objects. These are always between the same two objects. And what's interesting about that is because they're between the same pair of objects, these two interactions are linked together. And in fact, we can say the stronger the support interaction, the stronger the friction interaction will be. So we have this interesting link. Okay, well, what other kinds of interactions do we have? How many of us have ever been in a body of water, pool, the ocean? Feel a little bit lighter in that body of water, yes? Might even float in that body of water. Why is that? That's because you are interacting with the water. Interacting how? Well, we call this a buoyant interaction. We'll study that a little bit later in class. If you think back to the free fall lab that we did, we ignored something. We ignored an interaction. What interaction did we ignore in that free fall lab? Air resistance. Air resistance. That is another interaction. What is an interaction between? It's an interaction between the atmosphere, the air, and an object moving through that air. This is another interaction between two objects. We can count more and more of these, right? If you have a metal object near a magnet, you probably have a magnetic interaction. If you probe an object down to the atomic scale, you have interactions between the nucleus and the electron. You have interactions between the proton and the neutron. You have interactions between the things that combine together to give you a proton. Interactions are all over the place. And the wonderful thing is that when you can start to describe these interactions in their entirety, then you can make a prediction about its acceleration. You can make a prediction about an object's location. Once you know the interactions completely, you have a way to boil that down to making a prediction about where an object will be. And that's a powerful, powerful tool, being able to boil that down. Now, everything we've talked about so far, though, with these interactions, these pushes, these pulls, they have been what we call qualitative. Qualitative means without number. If we want a way to build these into some sort of terminology that we can make predictions about, we're going to need to apply numerical values. And to quantify these interactions, quantifying these interactions are done through defining this physical characteristic of force. We define this physical characteristic of force to be the quantified value of an interaction, to tell us how strong an interaction is. And how do we quantify this? Well, we've got this understanding that force should describe an interaction. And Newton's second law tells us something about interactions and something we've already quantified, acceleration, and something we've already quantified, mass. So if we take mass and acceleration, two things we've already quantified, and apply it to this new quantity of interaction, well, we can create something. So instead of saying interaction, I'm going to say force. Force represented with the letter F. We're still in this nice convenient realm of physics where letters make sense. That'll change soon. So we have this force F that we quantify, and we say that if the interaction is increased, then our acceleration should also be increased, right? Increased acceleration, or increased interaction, increased strength of interaction, means an increase in acceleration. So we define this force thing, to say that our force is our stand-in for interaction, so if interaction increases, well, that also makes forces. So we make this sort of daisy-chained argument to be able to start to quantify this value. Well, what else did we see? We saw that if you increase mass, you decrease acceleration. This is not a proportionality, rather this is an inverse proportionality. Yes? This is inverse proportionality that tells us acceleration and mass are inversely proportional to each other. So we have these two pieces. Again, we experimentally found these, right? We experimentally found these two things. We take these and we put them together. And we say, if this is true, then force divided by the mass should be proportional to the acceleration, yes? Just combining these two equations. Combining these two proportionalities tell us that force over mass is proportional to acceleration. Do we all buy into this? Any questions? Any thoughts? Now, we've talked about this before. If we want to take a proportionality and put it into terms of an equality, we have to insert a constant of proportionality. We insert a constant of proportionality that says force over mass is equal to some constant k times the acceleration of the object. Now here's the wonderful thing. We have yet to really define what that force F is. We haven't made a decision about the unit of that force or anything about that force. So what we can do is make the convenient decision, because it's not yet defined and there's no clear explanation of what this force might be physically. So we have the freedom to sort of choose what this is. And we choose a value of force such that this constant is equal to 1. We have that freedom. We have that freedom because this is a derived quantity. Force is a derived quantity. We have the freedom to choose a unit of force such that k is equal to 1, meaning we get force over mass is acceleration, or force is mass times acceleration. We might more commonly write it. And this is how you take that empirical law of Newton's second law that says if your interaction is larger, you have a larger acceleration. If your mass is larger, you have a smaller acceleration. This is how you take that empirical idea and build it into something that is quantifiable, something that has a number, a numeric value to it. Because you can have an object with some mass, you can have an object with some acceleration, you can determine numerically what the force is. And specifically, this is the net force. So I'm going to write net there to say this isn't just any singular force, but this is the combined force of the associated interactions acting on an object. So where does this leave us? This leaves us with Newton's two laws written with the equation at least his first and second law. Newton's first and second law can be rewritten with the equation that the net force is mass times the acceleration, with a caveat, not completed yet. Acceleration is a special kind of quantity. I heard someone say it earlier when I asked what we studied in physics. What kind of quantity is acceleration? It's change in velocity, but we have two special types of quantities in this class, right? We have something like time where direction is unimportant, and something like acceleration where direction is important. What do we call that? A vector. Acceleration is a vector because direction is important. Well, what about force? Is direction important with force? Yeah, probably. If I push an object to the left and I push an object to the right, I should expect different outcomes, right? Push an object to the left, it should move to the left. If I push an object to the right, it should move to the right. So force should also be a vector. What's interesting here, mass is not a vector. Mass does not have direction. Mass is just a physical count of how much matter exists in an object. So mass is a scalar quantity. Force and acceleration are your vector quantities. And since mass is a scalar quantity, that means your force, your net force, and your acceleration should always be in the same direction. All right. How are we feeling so far? Okay, we're about to dive into making this a little bit more mathematical. Because now we have Newton's laws. F equals ma. And this encompasses both his second and his first law, because we can see if the net interaction is 0, that must mean mass times acceleration is also 0. Well, mass is never going to be 0, so the only way is for acceleration to be 0. So that does encompass his first law too, F equals ma. So we can take this and we can apply it to an object. Specifically, let's think about the easiest application of this we can. We might consider the application in which we take an object, we hold it up high, and we release it from rest. What do we call that type of motion? What do we call it? Free fall motion, caused by gravity. Free fall motion, that's what I was looking for, free fall motion. We have free fall motion, which is caused exclusively by gravity. Remember, we defined free fall motion as being the type of motion that occurs when it's only under the influence of a gravitational interaction. So we have a free-falling object. Let's say we take that object I just dropped, and we say that that object I just dropped has a mass of about 20 grams. Yeah. That object I just dropped has a mass of about 20 grams. Well, gram is not the base SI unit. What is the base SI unit? Kilograms. So we want this in kilograms, not grams, so we need to do a unit conversion. Our unit conversion takes our 20 grams, we multiply it by a conversion factor. Let's go ahead and do this practice. We say 1 kilogram is 1,000 grams. 1 kilogram is 1,000 grams. With this unit conversion, that makes our 20 grams equal to 0.02 kilograms. And in fact, this is exactly 20 grams. So I should even probably write 0.020 kilograms for significant figures. Sound good? So we have our mass. What else do we know about a free-falling object? What was that? Acceleration. What do we know about its acceleration? Absolutely. Our acceleration is very well known for any free-falling object. Our acceleration for any free-falling object is 9.8 meters per second squared. Specifically, it's 9.8 meters per second squared downwards. So we'll even include that negative j hat just for completeness. Last time we were here, we found out we can kind of keep these separated. The I hats and the j hats there for our own note-taking convenience. But we can separate vertical and horizontal. We know this is completely vertical, so maybe the j hat should be done this. But that negative is important. That negative is important because it tells you it's downwards. Well, now we want to know what the net force acting on this is. Well, the net force here is caused singularly by the interaction of gravity, right? Because free-falling objects are defined to be objects that fall only under the influence of gravity. That means in this case, the only interaction The only interaction is a gravitational interaction. So we might substitute that in and say, well, we are specifically looking at the force of gravity. And we say, what is the force of gravity? Well, it's going to be mass times acceleration, 0.020 kilograms, multiplied by negative 9.8 meters per second squared, J hat. And that gives us the force of gravity. That gives us the force of gravity. Well, what does this end up equal? Take 0.02 multiplied by 9.8, what do you get? Break out your calculators. What do we get? What was an answer?
Negative 0.196.
Negative 0.196. What are the units? Kilogram meter per second squared. And is this vertical or horizontal? Vertical, absolutely, J hat. So we have negative 0.196 kilogram meter per second squared in the J hat direction. This is the quantified value of how strong the pull from gravity is. This is the quantified value of how strong the pull of gravity is. Now, this is an important quantity. Force is an important quantity. It's really important because why? Because it tells us how we can predict acceleration from an object. If you know the forces acting on an object, you can predict its accelerations, its changes in velocities, and its displacements. So it's really important. And because it's so important and we're going to be using it a lot, we don't want to have to sit there and write kilogram meter per second squared over and over and over and over. Run out of ink and pens too quickly. So we define a new unit. We say force. And I use square brackets here to say I'm not looking at the quantity, the numerical value. Rather, I'm just looking at the units. The units of force, yes, they're kilogram times meter per second squared. That is absolutely true. But we give it a new name. We give it the new name of a Newton, represented by a letter N. You give it the new name of Newton, named after the fig Newton. No, named after Isaac Newton. We give it the new name of Newton that replaces just this kilogram meter per second squared. So instead, we can rewrite this as about negative 196 newtons in the J hat direction. That seem all right. Any questions? It's not so bad, right? Not so bad. Now I'm going to erase most of this. I'm going to erase most of this, and specifically I'm erasing all of the numerical parts. So you scale back. Why do I do this? I do this because I want to make something a little more generalizable. I want to make something more generalizable. And what we can say is instead of saying the mass is 20 grams, well, the mass is just M, whatever that value is. It's a standard. It's a variable. If we have any object, we could put in its mass. right? And then we look at our acceleration. Well, we know our acceleration is always negative 9.8 for an object in free fall. Always. And since that 9.8 is used so often, we give it a new letter. We say acceleration for an object in free fall is negative g hat. G is a stand-in for the 9.8 meters per second squared. So we know that this is the acceleration for any object in free fall. We come down here. Our net force is still the force of gravity, in which we take what was our 20 grams and what was our 9.8, where we take those and we now just input the variable letters, m, g, j hat. And this quantifies for us the gravitational interaction between the Earth and any object. The gravitational interaction is quantified by force of gravity as negative mgj hat. Oftentimes, we like to talk about the magnitude of the force of gravity. Remember, for a vector, if we put the absolute value signs on the outside, we're talking about the magnitude of this vector. The magnitude of the force of gravity. And if we were lazy, we would just write the vector quantity without the arrow on top. The magnitude of the force of gravity can just be found by taking away the directional components of the equation we just derived. And then from here, we know empirically that the force of gravity is downwards. Anytime I've dropped an object, the force of gravity has always pulled it downwards. I've never seen the force of gravity push an object up. So we have the magnitude, the direction is downwards. And why do we like to write it this way? Well, we like to write it this way because on occasion, we do like to flip our coordinate system to say downward is positive, in which case our force of gravity would be positive. But it still means downwards. Earlier, someone had mentioned this idea of weight and interaction. Weight. What is weight? Well, coincidentally, weight is your force of gravity. Weight means the same thing as your force of gravity. So if you hear this word weight, what does it mean? Weight just means the force caused by the interaction of gravity. You step on the scale, right? You step on the scale, and perhaps your scale reads that you are, 200 pounds. It's a little bit under what I am. So perhaps you step on the scale, it says 200 pounds. Pounds. What is pounds? Pounds is a unit of weight. Pounds is a force. Pounds is a unit of force. It's also a unit of money if you're in the UK. But for us, pounds means it's a force. There's a conversion between pounds and newtons that exists. It's something like 0.22 or something like that. Newtons is a pound. I don't remember it off the top of my head. But there is a conversion factor. The difference, though, is that pounds is the imperial unit of force. Newton is our SI unit. We will stick with newtons for this class. The weight is your force of gravity. All right. Do we have any questions? Any thoughts? All right, let's talk about a more complex system, although maybe not much more complex. I take this cart. This cart has weight, yes? It still has weight when it's right here. It still has weight when it's on this table. All of that is true, right? That cart has weight, but it is not accelerating. It is not accelerating because the net interaction is zero. It is interacting with stuff still, but its net interaction is zero. How might we describe the different interactions going on here? Well, for our cart on the table, We might analyze this system by saying there are two interactions going on here. There's an interaction of gravity and that support interaction, right? We say it has weight and it is interacting with the surface that is supporting it. So what we are going to do here is add that support interaction, but we give that support interaction a name. Because when we quantify it, we now have a force, and we give that force a name. We call it the normal force. The normal force is the quantified description of that support interaction. So when you talk about that normal force, what you're talking about is the interaction of the table supporting whatever object it is supporting. In this case, the cart. Now you ask yourself, well, why the name normal force? The name normal force, and this is an important caveat, the name normal force comes from this mathematical term of normal. The mathematical name, or word for normal, what this means is perpendicular to a surface. In mathematical terms, when you hear the word normal, it means perpendicular to a surface. In this case, our surface is this table. The normal force is always perpendicular to the surface. In this case, the surface being the table, the perpendicular is going to be either upwards or downwards. But in this case, the cart is above the table, so upwards. The normal force is always perpendicular to the surface that we are analyzing in that surface-object interaction pair. The normal force is always perpendicular to the surface. Does that seem all right? All right, well, how can we quantify the normal force for this cart? This cart, the cart has a mass of about 150 grams. The cart has a mass of about 150 grams. What we can say is that the net interaction is going to be the combination. The net interaction is going to give us a net force, which is a combination of the force of gravity, we can also call that the weight, as well as the normal force. So we say it is a combination of the force of gravity and the normal force. Does that sound good? Well, given the mass of an object, you can always find out what its weight is. You take that mass, you convert it to kilograms, you multiply it by 9.8 meters per second squared, and you can get the weight of the object. So the force of gravity is something we can find. Okay, we check that off the box. Then we look at it and we say the net force. Well, what do we know about the net force acting on this cart? What do we know about the net force? Well, we look at it. We say, what's its speed? We give it a couple of seconds. All right, what's its speed now?
0.
So its acceleration is?
0.
So what do we know about the net force?
0.
It's 0 as well. So for the cart resting on the table, we can say 0 is equal to the force of gravity plus the normal force. Does that seem reasonable? Yes? So now we have that 0 is the force of gravity times the normal force, or in other words, normal force is equal to negative force of gravity. Just subtract the force of gravity over to the left-hand side. Do we see how we got this? Yes? Well, normal force then is equal to negative the force of gravity, which is negative mg j hat. Yes? The negatives cancel out. That means the normal force is equal to mg j hat. Since it's in the positive j hat, that indicates what direction? Vertically upwards, right? Positive j hat means vertically up. And vertically up is perpendicular to the surface, as the mathematicians would hold true with that word normal. So we are perpendicular to the surface, vertically upwards. And in fact, it's important that it's upwards because what cancels out down? Well, down is canceled by up. So we have this normal interaction derived from this weight. Now, is this always going to be the quantity of normal force? Can we say that a normal force can be calculated by taking the mass, multiplying it by the acceleration due to gravity? Not always. Not always. While this force is always described, while the gravitational force is always described by the mass times the acceleration due to gravity, put a caveat here, while near Earth's surface, that is always true near the Earth's surface, this equation is not always true. In fact, we'll talk about how to generalize out all of this information. But I just want you guys to remember that some interactions will have forces that we can create an equation that will always describe it for us. Some interactions we can. Other interactions we cannot. The normal interaction, applied pushes and pulls, tension. These are things that we don't have one set equation for. We'd have to go through the process of analyzing a system to find values. Other interactions, the force of gravity, electric forces, even atomic forces, they have set equations that we can use. And we'll go through and we'll see more and more of these. All right, do we have any questions, any thoughts? All right, this takes us to being about 10 minutes left. So in these last 10 minutes, I wanted to take a stop and talk to you guys about what's going to go on with the class moving forward. So for this week, you do not have a problem set. Why do you not have a problem set? Because something very important is happening Wednesday. Can someone remind me what Wednesday is what's happening on Wednesday? An exam, absolutely. So we have an exam coming up on Wednesday. I really want your focus to be on studying for that exam. So I'm going to give you guys a little bit of break when it comes to homework. Your next problem set will be on forces and interactions. So next Monday we'll talk more about these interactions. But you don't have a homework set for this week. This week you just are going to be focusing on the exam. For your exam, you will be given the entire lecture period to solve a couple of problems. There will be a problem on linear kinematics, meaning straight line motion. Could be accelerating, could not be accelerating. That's going to be the mystery of that one. You have a rotational object problem. You'll have a projectile problem. I am expecting you to be able to break a vector down into components. And I'm expecting you to be able to do some unit conversions. The equations on your note card are enough to solve any of the problems that I am going to be giving to you. You will notice on your note card you are not given that fancy range equation, the V0 squared sine 2 theta over g, right? We've discovered this, yes? Why are you not given this equation? Well, because it's only sometimes true. That range equation, that is V0 squared sine 2 theta over g, is only true under very limited circumstances, and I exclude it from the equation sheet because every time I include something like that, students try and use it in a place where it does not apply. So you are not given that equation, but the good news is that that equation wouldn't apply to the problem I'm planning on giving you anyway, if that is a hint as to what kind of problem to expect for projectile motion. What else? For the test, you'll be allowed those note cards at the beginning of the class. I'm going to be checking those note cards to make sure there are not any additional notes on them. So you cannot write on them, you cannot add any equations to them. What you are given is what you are expected to be able to use. You are allowed to bring headphones and listen to music while you guys are taking the exam, but you'd be warned that you cannot change your playlist halfway through the test. Your phone is to remain away during the test. So whatever playlist you pick, I hope you like it. Calculators, you can bring any calculator you'd like. That is up to you. I will have scratch paper here for you to use during the test. And bring a pencil and eraser. Usually I bring a couple extra pencils and erasers, but if you guys, if too many people forget them, then I don't have enough to go around. Okay. Are there any questions about the test? Yes?
Also, on Wednesday we meet here, I think, Sanford, right?
No, you still go to lab this week, right? The exam will take place after lab. Any other questions? So the exam will be 11 to 12:15. All right, any other questions? Yes?
So does that mean there's only like 4 questions and we have the whole class, like 4 or 5 questions and we have the whole class period to solve it?
Well, I believe I just gave you an indication on to exactly how many questions there are. But sure, you can assume that there are only a few questions. All right, any other questions? Yes?
How many points is your exams? 100?
So, don't focus so much on the points, right? Because the points are kind of arbitrary. As far as to what percentage of your grade this counts to, that's on the syllabus. I can't remember the exact percentage. The problems will be graded though, as far as like the points and everything work out. The problems will be graded such that you earn partial credit for partial attempts, so please do not leave anything blank. But the actual numerical value of points is going to be arbitrary, so don't worry too much about that.
So will we need to memorize that like the velocity initial of x is equal to the velocity initial of cosine theta? And then incorporate that?
If you pull out your little sheet of notes, your little note cards, you can flip to the vector section. And the vector section says the x component of the vector is cosine theta of the magnitude. So you have that equation. If you want to take the time to memorize it, it can't hurt. But that is one of those vector questions, I think, on the pink sheet.
Wait, can you repeat that? So on the vector.
So if you look there, it should say cosine theta is equal to x component of a vector over the magnitude, right? That is that same equation. All right, any other questions? Yes?
So is problem set 4 still due on Wednesday?
Do you guys want an extension on problem set 4? Okay. There's a projectile problem on there. I recommend trying to attempt them. It's good studying. I will give you guys until Monday to get the problem set 4 done. Sound good? All right. Yeah, sure, why? Any other questions? I'm feeling particularly generous if anyone has any other comments, concerns. Oh, and another note, lab, I announced it to my Monday lab already, but lab this week, it took a little bit longer than I expected for some groups. So we're going to do the projectile lab for this week as well as next week, so it's going to end up being a 2-week lab. Those of you in Wednesday lab, just be prepared for that. It's going to, you're going to have 2 sessions to finish it. Do you have a question?
So not due today,
Just wait until Wednesday when you have lab and I'll explain it. All right, any other questions? Yes?
Just one more time, linear, projectile, rotation.
Those are the big topics that we've talked about this so far. I do expect you to be able to break vectors down into components. I do expect you to be able to do unit conversions that may be built into these problems. Any other questions? All right, wonderful. If you guys want to stick around, I'm going to be doing a brief recap on kinematics and the stuff that you're going to need to know for the test. But if you guys are good to go, you're free to head out. I do also have your homework 3s if you want to pick those up. Just do so at the front of class. Homework 3?
Yeah.
Okay. And you did email me, right? Blair?
Yeah.
having to do it.
Oh, word.
All right, homework 3 is at the front of class. If you want to, come grab your graded work.